Hi there again. We're going to talk about rates of reaction in this section. So we're going to talk about what we can do to make a reaction happen slower or faster. And so I don't know if you've ever heard of MREs, meals ready to eat. So they look like that, and they have a chemical reaction in there when the soldier activates this. It will heat up the meal for them so they can eat a hot meal. So MREs. And all that is happening because of the chemical reaction. So let's see if we can change that rate. So rates of chemical reactions are expressed by how much the amount of reactant changes per unit time. So you know a rate is how fast something's going, so it's the distance divided by time, that's a rate. So we're going to have something similar, we're going to have a change over time. So if we were looking at the number of moles changing from reactant to product, we could measure how long that takes to happen in moles. So here's time changing, and so we have reactants changing to products. So we can measure that rate, how fast that's happening. So we'll talk about that in a sec, but the way we have reactants changing into products is because of collisions. So if atoms or ions or molecules have enough kinetic energy, they can collide with other species, and then they can form into a product. But they have to have enough kinetic energy, and they have to hit in the right orientation for that to happen. So we need effective collisions with enough force. So how fast they're moving is the force, and they have to be oriented the right way for this to turn into a product. So here's our reactants on the left side. They're hitting in together like that, and if they hit correctly in the right orientation, they will form the product that we want. Okay, so this is hydrogen diatomic, oxygen diatomic. If they hit in this orientation, then they can turn into water, H2O, H2O. So that's an effective collision because they're facing in the right orientation and they have enough energy when they hit to form something new. That's an effective collision. Ineffective looks like this, where the reactants are not oriented the right way, they're not hitting in the right way, so they just bounce off each other and they don't form the product. That's an ineffective collision. So for this to happen, the reactants have to have enough force and they have to be in the right orientation. So reactants start here on the energy diagram, and this is time. This is how much energy they have. So they start here. They have a certain amount of energy. They have to get over this energy hump in this diagram to get to a product. So when they get to this part, they are hitting into each other, and they haven't made the product yet, but they're hitting together and they're in one big smushed form in the right formation, like we just showed you. Well, like I just showed you, in the right orientation. When they hit like that and they're squished together, it's called an activated complex. The energy that's needed for this to happen is called the activation energy. So if these guys have enough energy and they get to this, they have enough energy at the top here in their activated complex, then this can all work out right, and then they're gonna then do a collision, and then they're gonna break into pieces into the water that they were forming into products. So the products have less energy than the reactants. So when you release energy like this is an exothermic reaction that we're showing you. The energy it takes to get to this activated complex is called activation energy. So when your reactants are higher up than your products, you're going to release energy, and this is exothermic. Activated complex is an unstable arrangement that forms for a little bit before they break into the right products. And that's sometimes called transition state or activated complex. So what 4 factors are going to affect how fast we can have this happen? We have to look at temperature, concentration of reactants, particle size of the reactants, and if we are going to use a catalyst or not. So first one's temperature. This is why we store stuff at low temperatures in the fridge, because we can slow this chemical reactions caused by microbes, and that ruins the food. We can look at concentration here. If we have this glowing piece of wood in regular air, it looks like that. As soon as we increase the concentration of oxygen in this bottle, we have a much better flame. Okay, so increased concentration will help the rate. If we have really small particles, we can make things happen so fast that it becomes an explosion. So you have to worry about this in areas where you can have dust. Any kind of dust, metal dust, grain dust, any really small particle sizes, if the conditions are right, they can explode. So you have to be careful with that, with dust, with lots of dust. So this was our original situation we just talked about. And we had reactants had a certain amount of energy. They need enough energy to hit correctly and form into that activated complex, and then they will break apart and turn into the products. If we can throw a catalyst in here, then we need a lot less energy for those reactants to turn into the products. So this is the energy diagram with a catalyst. Oops, sorry. And this is the energy we need if we don't have a catalyst. So it takes a lot more energy, so it affects the rate. So we can, instead of having a catalyst, we can put something called an inhibitor. It's the exact opposite of a catalyst, to slow chemical reactions down. So a lot of antioxidants, antimicrobials are put into foods to slow chemical reactions. And let's see how much you got out of this. So look at that, try to figure out what the rate would be. Okay, so we measured in millimoles per second because we're looking at concentration over time. So that's the only one that had a time in there. In a chemical reaction, the energy of reactants is always, so this one is talking about activation energy. Activation energy is always higher than the reactants. An increase in which of one of the following will not increase reaction rate? So what will not increase the reaction rate? So it doesn't matter how much reactants you have. Catalyst works by doing what? This is a good question. So it lowers that activation peak, so it makes it easier. Alright, so I hope you got something out of this. This is the important section, and I'll talk to you soon. Bye-bye.